Hello everyone. Today in this session we will see what is a thick cylinder, what are the design aspects involved while designing a thick cylinder, what will be the stresses induced in a thick cylinder, and we will see an equation which can be used to design a thick cylinder which is made up of cast iron. Now before starting, let us discuss what is a pressure vessel. Now pressure vessel is any component or device which is used to handle fluid under pressure. For example, the LPG cylinder that you have in your household is a type of pressure vessel which is handling your gas or the fluid at a certain pressure which is above the atmospheric pressure. Similarly, the steam turbines can be treated as a pressure vessel. The boilers that are used in order to generate the steam can also be treated as a pressure vessel. The condensers where you reduce down the temperatures at certain pressure, that can be also treated as a pressure vessel. Apart from this, you can treat the heat exchangers also as a pressure vessel, where you have different types of fluid being flowing under pipes. So those pipes also can be treated as a pressure vessel. So any device which is subjected or which is handling fluid at certain pressure can be treated as a pressure vessel. Now pressure vessels can be divided into different categories. Now one of the major classification comes from the shape of the pressure vessel. So according to the shape, when we try to distinguish the pressure vessels, then it is cylindrical pressure vessels and spherical pressure vessels. In some cases you may find the conical pressure vessels as well. Now in cylindrical pressure vessels, we have again two subtypes. One is the thin cylinders and other one is the thick cylinders. Now as the name suggests, cylindrical pressure vessel, so here the pressure vessel will be in the form of a cylinder or a tube which will be handling the pressure or the fluid. Now what is a thick cylinder and what is a thin cylinder? In case of your thin cylinders, the ratio of your mean diameter to the thickness of the cylinder will be greater than 15. So your diameter will be far larger than your thickness of the cylinder. In some cases or in some books, you will find that this can also be taken as greater than 20. So some books distinguish it as d by t greater than 20, then they will treat it as thin cylinder. When the thickness is considerable as compared to the diameter, means when the d by t ratio is less than 15 or less than 20, then in that case the cylinder can be treated as a thick cylinder. Now let us discuss what will be the stresses which will be acting on a cylindrical pressure vessel when it is subjected to certain pressure. So here in this figure I have shown you a cross section of a cylinder, a thick cylinder pressure vessel, where the diameter and the thickness ratio is less than 20 say, or the thickness is considerable enough so that it cannot be neglected. So in this case here your thick cylinder is subjected to an internal pressure say Pi and to an external pressure say Po. This can be a case of an heat exchanger tube where the inner tubes will carry fluid at certain pressure and out on the outer side they will be surrounded by the other fluid to take away the heat. Or this can also be treated as your two concentric shafts in case of your press fitting operations. So this may be the collar and this may be treated as a shaft. So when press fitting operations are being done, there is an internal pressure being developed on the system. So that can also be treated as a case of a thick cylinder. Apart from this, you can consider this as a tube carrying certain fluid which is at a pressure lower than the atmospheric pressure. In that case, the atmospheric pressure will act from outside and there will be some pressure inside which will be lower than the atmospheric pressure. Now if such a case happens, means when a thick cylinder is subjected to an internal pressure as well as an external pressure, then at any point along the thickness, at any point if you consider, there will be some stresses occurring. Now what will be those stresses induced? Suppose at point A. At point A there will be three types of stresses which will be induced. At this point A we have considered it at a radius of small r. So at a radius of small r we have considered a point A. In that case at this point there will be three stresses induced. Those three stresses are tangential, radial and axial stresses. So one will be tangential stress, other one will be the radial stress, and last one will be the axial stress. In case of your tangential stress, it will try to split apart your cylinder into two pieces. So from here it will try to break into two pieces, or from this side also it can break. So a similar figure you will see in case of your tangential stress, it will try to split open into two pieces. In case of your axial stress, this will try to elongate or cut along the length of the cylinder. So this stress will try to cut the cylinder, or this force will try to cut the cylinder into two pieces along the length, and that will induce a stress in the cylinder which will be called as the axial stress. Here a force will try to cut apart the cylinder along the radius direction, and that is called as your tangential stress, and in some books it is also mentioned as the Hooke stress. Now last one is the radial stress, which will be the compressive force or the compressive stresses which are acting at this point and this point. So radial stress will be the compressive stress due to this pressure acting on the edges of the cylinder. So there will be three stresses: tangential, radial and axial. Tangential will try to split apart radially, axial will try to split apart along the length direction, and radial will introduce a compressive force or a compressive stress. Now what will be the values of these stresses? So we won't derive the equations here, rather we will directly use it from the data book. So when you try to see there on 6.15, you will find this equation there. But before that, let us see what are these stresses. So if you try to plot these stresses, the axial stress will be along this direction, along the length direction. The tangential stress will be along the radial direction, so I have shown it here. And the radial stress is compressive, so it will be along the x direction here. So there are three stresses. One is the axial, the other one is the tangential or the Hooke stress, which is trying to split up the cylinder into two pieces along the radius direction. Other one is axial, which is trying to elongate along the length direction, and the last one is this radial, which is along this x direction. So if the 2D nature of stresses is plotted, you will see something like this. And on each of these planes, wherever these stresses are occurring, you won't find any shear stress. That you can imagine by drawing a square on a balloon, and if you try to blow up the balloon, then what will happen is this: if you have drawn a square on the balloon, then the size of the square will increase, and rather the shape won't get distorted. Means it won't get distorted like this. It will remain, means if the square is like this on the balloon, it will magnify just in this shape. It won't get distorted. And whenever there is no distortion, means no shear stress is involved. So on these planes, only these stresses will occur, and such planes where only normal stresses are occurring and no shear stresses is occurring, those planes are called as the principal planes, and the stresses associated with them are called as the principal stresses. So in a way, your Hooke stress is a principal stress, your axial stress is also a principal stress, and your radial stress is also a principal stress in the third direction. So there are three principal stresses. One is your Hooke stress, other one is your axial stress, and other one is your radial stress. This I have shown you only the 2D case. In 3D case, there will be three: sigma T, sigma A and sigma R, which are all of them are the principal stresses. Now if you want to find the shear stresses, there will be shear stresses induced, but on the other planes, not on these planes. So to find the shear stresses, we can apply the Mohr circles theory, and you can find the shear stress induced easily. Now coming back to the equations, what will be the stresses, the magnitude of these stresses induced? So these equations you will find for each of these stresses, you will find it on PHG 6.15. We are not deriving these equations here. We will be directly using it from the data book. So you will find this equation there on data book on 6.15. This is your tangential stress, or some books also specify it as your Hooke stress. So tangential stress in case of your thick cylinder, which is subjected to internal pressure as well as external pressure. Internal pressure was Pi, external pressure was Po. Internal radius was Ri, external radius was Ro. So for that you get this equation. If you see, this term is a constant term here, because Pi and Ri are constant, Po and Ro are constant, because Ri and Ro are your internal and external radius. Here if you see, there is a variable term which is R. So this is stress at any point in between the thickness of the cylinder. So at any point, any location if you want to find, means here, the radius from here will be different From here it will be different up till here, it will be different up till here, it will be different up till here, it will be different. So it is at any point the distance of that point is r here, which is being mentioned here. So here in this equation only variable here is r. This entire thing is constant. So this will be a variable. Since this r is variable, this entire term becomes now variable. So what you will have, the tangential stress as this constant value plus this variable value. And as r will go on increasing, this term will go on reducing. Means r at inner periphery will be least, on the inner side it will be least. Means here r is smallest, so this term here will be largest, because since here r is smallest, we are dividing by a smaller number, so this will be larger. So some constant plus larger number means it will be highest on the inner periphery, and on the outer periphery it will be maximum. So this entire term will become minimum on the outer periphery. Means this variation of the tangential stress will go on reducing. Means at the inner periphery it will be maximum, and on the outer periphery it will be minimum. Now suppose it is subjected only to internal pressure. In that case what will happen? Let us see that equation. So when external pressure is 0, so PO becomes 0, this term vanishes out, here PO vanishes out, and what remains is Pi Ri square over Ro square minus Ri square, and here Ri square Ro square over R square into Ro square minus R square. So let us see, it will be this equation, and now you can take this entire thing common from both the two equations. So when you take common, you will get this term. This is a constant, and again I have told you this is only the variable here. So depending upon this term, the value of stress will vary. So you get the tangential stress or hoop stress as this, which is this value, Pi Ri square over Ro square minus R square, 1 plus Ro square over R square. As R will increase here, this value will decrease, and as R is reduced, this value will increase. So on the inner periphery R will be Ri, and this value will be least, and in R will be Ri, and this value will be maximum. Ro, this is maximum value, say 50, and Ri is say 25. So in that case this will be 2, and as you move away towards Ro, R will become Ro, so 50 by 50 will become 1. So means on the inner periphery it will be maximum, and on the outer periphery it will be minimum. So if you try to plot the variation, what you will see, on the inner side the tangential stress will be maximum, and on the outer side it will be minimum. Since we are adding it up, both will it will be on the positive side only. So you will get the variation something like this, okay, or maximum on the inner side and minimum on the outer side. Now next one was the radial stress. Let us check what is the value of the radial stress. So radial stress is this equation which is being mentioned on page 6.15. Now again, if you see the equations, the two equations for your tangential stress and radial stress, if you see, observe the two equations, this term and this term is same here. Both these two terms are same. Here also these terms are same. This term and this term is same. The difference here is for your positive and negative side. So here there is a negative sign, and here there is a positive sign. So again, for external pressure to be 0, I can redefine this equation. So this external pressure becomes 0, say suppose. So in that case you will get this equation, and on modifying what you will get is Pi R square over Ro square minus R square into 1 minus Ro square by R square, 1 minus Ro square by R square. Now as R goes on increasing, this will tend towards 1 and this will become 0. Means at the outer radius, when R equals Ro, this will become 1, this ratio will become 1, and this will become 0, 1 minus 1 will be 0. So radial stress will be 0 on the outermost periphery, and it will be maximum on the inner periphery, because here Ri will be least on the inner periphery. So when you try to plot the variation, what you will get, since here it is reducing, what you will get is the variation will be compressive or negative side, on the negative side. So it will be something like this. So for external pressure to be 0, on the outer periphery it will be 0 here, and on the inner periphery it will be maximum. This is your variation of the radial stress. We have seen the variation of the tangential stress. It was something like this, maximum on the inner periphery and some value on the outer periphery. For radial stress it is maximum on the inner periphery and 0 on the outer periphery. These were for the conditions where pressure on the outermost pressure was 0, only this cylinder was subjected to internal pressure. Last stress was your axial stress. This axial stress comes out to be this value, Pi R square minus PO R square over Ro square minus R square. Again this equation is on page 6.15, you can find there. And for pressure, external pressure to be 0, PO to be 0, what you will get? The axial stress as pi r square over r square minus r square. So here pi is constant, ri is constant, ri again r also constant. So this stress remains constant throughout. It is not the function of your radius. So axial stress remains constant. Obviously axial stress was acting along the length direction, so it won't be the function of your radius, so hence it remains constant. So three stresses we have found: axial, tangential and radial. Tangential is variation is maximum at inner periphery, minimum at the outer periphery. Radial is maximum at inner periphery and 0 at the outer periphery, and axial remains constant. Now we will try to find out the critical point where the stresses will be maximum in case of your thick cylinders. So where will be the critical point? So let us see. Your variation for the tangential stress was something like this: maximum on the inner periphery and minimum on the outer periphery. Your radial was something like this: maximum on the inner periphery, minimum 0 on the outer periphery, and axial was constant. So suppose 2D case if we consider, in that case the variation at the inner point, there was some tangential stress and some radial stress. At inner point, tangential stress as well as radial stress, but in negative direction. So two values, one positive and one negative. When you try to draw a circle, it will be some bigger circle, and the maximum shear stress induced, because ductile material failed by the yielding occurs due to shear of the material. So here what we'll have is shear stress induced will be sigma 1 minus sigma 2 by 2, and minus becomes plus. Sigma 2 was negative of negative value here, so minus becomes plus, and what you'll have is tau max as sigma t plus sigma r by 2. At the outer radius, what you'll have? At outer radius, radial was 0 and tangential stress was some value, so you will get sigma r is 0 and sigma t is some constant value, so tau max will be tau sigma t by 2. So obviously your critical point in these two cases, here the stress will be maximum and here it will be less. The shear stress at the inner point will be maximum, and at the outer point it will be lesser than the inner point. So obviously your critical point is the inner radius. So in case of designing, we will consider the inner radius while designing the pressure vessels. Okay. So now let us discuss what will be the stresses in the thin cylinders as well. We are not going to study thin cylinders in this course, but still let us see what will be the stresses. So in case of thin cylinders, your variation is very less, means the difference of your radius is very less, and your thickness can be written as Rho minus Ra. Using the same equations, this was the tangential stress for a thick cylinder subjected to only internal pressure, which we have derived, which we have seen from the data book. So in that case, here if you take R, Ri, Ro and R will be almost the same. The radial distances are very less, the thickness is small, so radiuses can be treated almost equal. So Rho by R will be almost equal to 1, so this will be 1 plus 1 will become 2, and this Ri we will take it as R, and we can write this as Rho minus Ri as A minus B, A plus B, so it will be Rho minus Ri, Rho plus Ri, and this 1 plus 1 becomes 2, this is R. Rho minus Ri can be taken as your thickness. Okay, it won't be equal to 0, so it is thickness, and Rho plus Ri will be almost R and Ri are almost same, so this will become 2R. So 2 cancels out. What you will get is an R and 1 R from here cancels out. What you will get is Pi into R over T, and R can be written as D by 2. So it will be PD by 2T. So this is your hoop stress, which you must have derived earlier as well in your strength of materials course. So it is the same thing in case of your thin cylinders. And for radial stress also we can do the same. This was the equation for radial stress subjected to only internal pressure. Now Rho and R are almost same in case of your thin cylinders, so this will be equal to 1. 1 minus 1 is 0, so radial stress comes out to be 0. So in case of your thin cylinders, your radial stress, the radial stress was the stress which was trying to create a compressive force. If you remember here, the compressive stress, this radial stress is 0 in case of your thin cylinders. And now the axial stress, let us see the axial stress. Axial stress was this value, Pi into R square over Rho square minus R square. This can be written as Rho minus Ra, Rho plus Ra. Ra can be taken as R, and Rho plus Ra can be again taken as 2R. So R and R cancels out, 2 remains here. P into R over 2T you will get, and R can be written as D by 2. So you will get sigma as PD by 4T. So this is your longitudinal stress or your axial stress for your thin cylinders. So to summarize, for thin cylinders, what you will have, your hoop stress or the tangential stress will be PD by 2T. There won't be any radial stress in thin cylinders. In axial stress, it will be PD by 4T. Yeah, the variation of the tangential stress will occur, but it will be very small enough. So if you try to plot the variation will be very small, and that can be almost taken to be equal. So if you try to plot the variation of the tangential stress, it will be almost equal. So we do not consider the variation here in case of the thin cylinders. So both the tangential stress as well as axial stress, we assume it to be constant only. Radial stress is 0 here, so that can be neglected. So here we consider these two equations, PD by 4T and PD by 2T, and these are constant values that we assume. This is always a constant, but here there will be slight variation in case of your tangential stress, but that variation is very small enough and that can be neglected. Now let us see an equation which can be used to design your thick cylinders subjected to only internal pressure made up of cast iron material. Now when the material changes, we have to apply different theories of failure that you know. In case of your ductile materials, we use either the maximum shear stress theory or the von Mises theory. In case of your brittle materials, we use the maximum normal stress theory. So here we are focusing only on the cast iron cylinders. Hence, we will be focusing only on maximum normal stress theory. So different theories, using different theories, you will have different equations. So there are other equations apart from this Lami's equation. One is your Bryan's equation and another one is your Calvin-Arrow's equation. So those are for your cylinders made up of ductile material. But we are focusing in this course only on cylinders made up of brittle material. So we will be using only the Lami's equation. Now we know, let us derive this equation. Now we know that the radial stress, tangential stress and axial stress values in case of your thick cylinders that we have derived. And that values I can write it on the inner radius. Why on the inner radius? Because we have seen the critical point was the inner radius was the critical point. By this Mohr circle, we have seen that the inner radius was the critical point. And we have seen the equations as well. This was your radial stress equation. And then again, this was your tangential stress equation in terms of R. This was your radial stress equation in terms of R. And axial stress was constant. So those equations we are rewriting here. So rewriting those equations on the inner radius, because inner radius was the critical point. What the maximum normal stress theory states, your component will fail when the maximum normal stress exceeds the maximum normal stress of the material at the yield point when the yielding starts. So using that theory here, now these are three principal normal stresses which will be induced at the critical point, which is the inner radius. So at the inner radius we have written that critical in terms of the critical point, or in terms of your inner radius we have written the equation. So everywhere wherever there was R, we have replaced it by Ri. So this was, if you remember, R square by R square. So there it becomes Ri. Here also it was R square. So it becomes Ri. On the inner radius we have written. And axial was constant. So these are your three equations. And what you'll see is, out of these, if you see, this term here is positive and this term here is negative. So if you try to see here, this value is constant in each of these three terms. So this value, if you see, is constant, and here if you are adding some value, here you are subtracting some value. So your tangential stress or hoop stress will be maximum, and then your axial stress will come, and less than the axial stress will be this, because you are subtracting something from this value. So here it will be something like this: sigma T will be greater than sigma A, and then sigma R. So you will have three normal stresses. First principal normal stress will be sigma T, which is your hoop stress, then will be axial stress, and then will be your radial stress. Now by the normal stress theory, maximum normal stress induced should be less than the normal stress in the material when the yielding starts. So for that case, what we will do is we will select which normal stress, which we will select this normal stress, which is this sigma T. So sigma T I will rewrite again at the inner point. So pi Ri square over Ro square minus Ri square, 1 plus Ro square by Ri square. Now we will try to rearrange this term. We will take pi on this side. So sigma T by pi will be Ri square over Ro square minus Ri square. Again, what I can do, I can shift Ri here, and I will have Ri square plus Ro square over Ri square. So Ri and Ri cancels out. what you will have is sigma T by Pi as Ri square plus Ro square over Ro square minus Ri square. We can rewrite this in terms of d, so it will be di square plus do square, do square minus di square. That constant because of di by 2 will cancel out from both the sides, from the numerator as well as the denominator. So you can rewrite it in terms of diameter. So it will be do square plus di square over do square minus di square. Sigma T by Pi will be do square plus di square over do square minus di square. Now this can be taken as A, this can be taken as B, this can be taken as C, and this can be taken as D. So if you remember, by componendo dividendo means by if A by B equals C by D, then I can write A plus B over A minus B can be written as C plus D over C minus D. So the same thing we are doing, componendo dividendo we are doing here. Sigma T plus Pi, sigma T plus Pi over sigma T minus Pi can be written as di square plus do square minus do square minus di square. So sorry, we have written plus here, so it will be plus here. Do square plus di square plus do square minus di square over do square plus di square minus di square minus do square minus di square. The same thing we have done, A plus B over A minus B equals C plus D over C minus D. Componendo dividendo we are applying to this term and this term. Okay, so you will get this value. Now opening the brackets, what you will get, this di and this di cancels out, and here minus and minus will become plus, and it will be do square cancels out. So the equation that you will get will be this. On the numerator, what will remain from here, di and di cancels out. In denominator, do and do cancels out. So what will remain is sigma T plus Pi over sigma T minus Pi is do square over di square. So do by di can be written as under root of this term here. And now do is outer diameter, which can be written as di plus 2t. In case of your thick cylinders, if you try to see, if you try to draw the diameter like this, so this is your thickness from here to here, and the outer diameter is this one, do, and the inner one is this one. So di plus t means do can be written as di plus t means di plus 2t. We have written it here. So di plus 2t over di will be equal to this term. Now di we have segregated these two terms, so di by di will be 1, and this will be 2t over di. So 1 plus 2t over di. We can shift this 1 on the other side, so on shifting the 1 it will become minus 1 here. So 2t over di will be equal to minus 1 plus this term, or I can write t over di, this 2 also will shift, so it will be 1 over 2, and this becomes 1 over 2, and here also 1 over 2. So that 1 over 2 we have taken common, and what you get is this term, half under root of sigma t plus Pi over sigma t minus Pi minus 1. Okay, and now di we can shift it here, so t will be di over 2 under root of this term minus 1. And for safe design, we know this stress should be less than your induced normal stress. So applying FOS, it will be sigma t should be less than bracket sigma t. So for safe design, sigma can be replaced with bracket sigma t, and your thickness will become this equation. This equation is called as the Lami's equation. This equation you will find it in another form in terms of your radius in PSG on 6.15. So you can use that equation as well, which is in terms of radius, or you can use this equation as well, which is in terms of diameter. This equation you will find it on 6.15. Now let us see a design problem related to this. So we have to design or find the diameter of a thick cylinder, outer diameter of a thick cylinder, which is subjected to a pressure of 30 MPa. FOS is given and internal diameter is 250 mm. We have to use Lami's theorem because here the material being mentioned is cast iron. FOS is given, so let us write down what is the given data. Internal dia is 250 mm, pressure is 30 MPa, FOS 2, and the yield strength for this material, it is grey cast iron, so this is mentioned with a number. So here this number ultimately becomes your sigma ut, which is the ultimate tensile strength of the material. So sigma ut is 300 MPa. Allowable stress sigma t will be sigma ut by FOS, so it will come out to be 150. Now we have to determine the outer diameter. So to know the outer diameter, we should know the thickness as well. So to find the thickness, we will use the Lami's theorem, and in this course we are only focusing on cylinders made up of cast iron, so we will use only Lami's theorem. So Lami's theorem, this equation we have derived, and the same equation you will find in PSG on 6.15 in terms of radius, that also you can use. So we will substitute the values of the unknowns here. So di is 250, sigma t we have found out 150, and pi was internal pressure, so 30. So substituting the values and solving, you will get Ts 28. So we'll use Ts say 30 mm. Now we have to find the outer diameter. So outer diameter will be di plus t means di plus 2t. So di we have found, di was given, which was 250. So 250 plus twice of 30 will give you 310 mm. So that's the design problem for your thick cylinders. Now let us see another problem. Determine the stresses on inner radius of a thick cylinder with an outer diameter of 300 mm and inner diameter of 240 mm. Also determine the magnitude of maximum shear stress if the cylinder is subjected to an internal pressure of 30 MPa. So here we have to find the stresses which are being induced on the innermost point. So innermost point was the critical point, if you remember. So that at the critical point we have to find the stresses which are being induced, and at the same point we have to find the maximum shear stress as well. So we'll write down the given data. Internal pressure was 30 MPa, external pressure is 0, di is 240 mm, so Ri comes out to be 120 mm, do is 300 mm, Ro will come out to be 150 mm, half of the diameter is the radius, and thickness will be do minus di by 2, which will come out to be 30 mm. Now induced stresses at the inner radius. So if you remember, this was the radial stress. It is given on PSG 6.15 in terms of your radius at any distance r if you want to calculate. External pressure being treated as 0. So here there will be a term for external pressure as well, which will turn out to be 0. So this was the equation, if you remember. This will be the original equation mentioned on 6.15. So here external pressure is 0, so this becomes 0, and this term also becomes 0. So only pi will remain. So here the same equation which we have reshuffled and found out this equation after substituting PO as 0. So in this equation we'll have to find it R on the innermost point they have told us, on the inner periphery. So R will be Ri. So here we'll substitute R as Ri. So this equation will modify to Ro square over Ri square. We'll substitute the values Pi, Ri and the other things. Pi was 30, Ri was 120, Ro was 150. So 30, 120 and 150, 120 again, and here 150 and 120. So substituting all these values for all these terms, what you will get is radial stress as minus 30 MPa, means this shows that this is compressive. Next one was your tangential stress. So tangential stress was also in terms of your radius. If you remember, this equation was there. Again external pressure is 0, so this becomes 0. And this becomes 0. So reshuffling, what we got was this equation, if you remember. Pi Ri square over R square minus R square, 1 plus Ro by Ro square over R square. So here again on the inner periphery we have to find. So again R will become Ri in that case. So what you'll have this equation here as Ro square over Ri square. So this equation you will find on 6.15, and you can modify that equation. This major equation you will find, and you can modify it accordingly when external pressure is 0 or external pressure is given. So this major equation will be there, and in that if external pressure is 0, this will vanish out. So what you will have is this term in terms of R, and we have to find at inner periphery. So R will be Ri. So that we have done here. So R becomes Ri, and sigma t, now just substitute the values Pi, Ri, everything we know. Pi was 30, Ri was 120, Ro was 150. So sigma t what we get is as 136.66, which is positive, showing that it is tensile in nature. Now next one was the axial stress. So let us check the axial stress value. So this equation, again the same equation in terms of external pressure, it will be given on PSG 6.15. It will be this equation which is given on 6.15. Again external pressure is 0 in this case. So Pi Ri square over R square minus R square will be your axial stress. So that value we will use, and Ro value we know, Pi value we know, which is 30, 120, 150, and substituting what you will get is 53.33. Now maximum shear stress, we know that maximum shear stress will, for that we have to plot down the Mohr circle. Now we know maximum shear stress will be the difference of the maximum normal stresses, and maximum normal stresses are which one? Your radial stress, and the other one is this is on the negative side. It is less than axial, but it is on the negative side. So if you try to plot the more circle, what you will see is the largest circle will pass through sigma t and sigma r. So it will be sigma t minus of sigma r over 2 will be your maximum shear stress, and sigma r is compressive, so it will be minus will become positive, and maximum shear stress will come out to be 83.33 MPa. So your maximum shear stress will be 83.33 MPa in this case. We won't take the difference of sigma t and sigma a. Sigma t and sigma a are of same sign. So if you try to take the difference and you find, then in that case the shear stress will be less here, and the shear stress in this case, in the case of the larger circle, will be more. So we have to find the maximum shear stress, and so it will be this value.